In this video, we will learn the concept of resistance from the chapter Electricity, Class 10. So here, when it comes to resistance, resistance is an electrical property of the conductor that opposes the flow of electric current. You all know that the free electrons, let's say this red circle are considered as free electrons. These free electrons will flow through the conductor, right? But here you can see a white circled things. Assume that these are protons, nothing but positive charged particles. Usually in conductors, the positive charged particles remain at fixed position. They won't flow just like the electrons in the conductors. So that when these free electrons flowing through the conductor from one point to another point, this flow is opposed by these positive charged particles, right? These electrons will get collide with the positive charged particles and their velocity will get decreases, right? Sometimes they come to halt. So here you can see that the flow of these free electrons are opposed by these particles. So every conductor or every electrical resistor will have this property, that is resistance. So we can say that resistance is an electrical property of a conductor which opposes or which obstructs the flow of electric current. We call this property as resistance. Okay? Yes. Now, here you can see that the mathematical expression, already we have seen this mathematical expression for resistance. R is resistance, V is potential difference, I is electric current. The V by I ratio is resistance, right? We have seen this from the Ohm's law. And coming to the SI unit of resistance, the SI unit of resistance is Ohm, and it is represented with the symbol omega. Omega. Okay. Ohm is the SI unit of resistance. And formula for resistance is R is equals to V by I. Okay. And further, we will see what are the factors that affects the resistance. What are the factors that affects the resistance? First, the length of the resistor. We see how the length of the resistor will affect the resistance. And next, area of cross section of the resistor. That is nothing but thickness of the wire or thickness of the resistor or conductor, right? And next, nature of the material of the resistor. For different nature of the material of a resistor, we have a different value of resistance. Okay, we will see that. And finally, temperature. Temperature will also affect the resistance. Okay, these are the four factors that affects the resistance. We will see one by one how these affects the resistance. Coming to the very first one of these factor, we'll talk about length of the resistor. Let's say this is the first case. Okay, this is the first case. In this circuit, we have taken a resistor having a certain resistance. Okay, here let's assume that the L is the length of the conductor. L is the length of the resistor or conductor. Let's say here we have taken the resistor, right? So length of the resistor is L. This is the first case. And its area of cross section. This is the area of cross section. This is the area of cross section. Okay, let's say the area of cross section is A. And the temperature remain constant. The temperature is constant. Okay, we kept the temperature constant here. Now, let's say the resistance of this resistor is R. Assume that the resistance of the resistor taken here in the first case, whose length is L and area of cross section is A, and the temperature remains constant. Okay, its resistance is considered as R. Okay, now if you see the second case, the resistor what we have taken is of same material, that is the material of resistor what we have taken in the first case. The same material of resistor is taken in the second case, and the area of cross section of the second resistor is also same, that is A. And here also the temperature remain constant. But here you can see that there is a change in length of the conductor. Only factor that you see the difference between the first case and second case is length. Let's say here the length of the conductor is twice the length of the first case. In such a case, if you observe the resistance also will be double the resistance of the first case. So if the length of the wire or length of the resistor is doubled, let's say the resistance is also get doubled. So from this we can understand that resistance is directly proportional to the length of the resistor. Resistance of the resistor is directly proportional to the length of the resistor. If length get doubled, resistance also get doubled, keeping the area and temperature constant, and in both the cases the material remains same. Okay, now we got the relation. Resistance is directly proportional to the length of the conductor at same area of cross section and at constant temperature. Okay, this is one factor. And next, coming to the next factor that affects the resistance. Here you see that the resistors in both the cases. Let's say this is case 1 again. The resistor what you have taken have a length of L. The length of this resistor is L, and the area of cross section is A. Okay, let's say the resistance of this resistor is R. And next, coming to the second case. When it comes to the second case, the resistor what we have taken is having the same length, that is the length of first resistor and second resistor are same. But what difference you see here? Area of cross section, right? The area of cross section of the second resistor is double the area of cross section of the first resistor. And here the temperature remains constant again, and the nature of the material is same in both the cases. Now, the length, nature of the material, and temperature are constant in both the cases. But here there is a change in area of cross section. Let's say the area of cross section of the second resistor is twice the area of cross section of first resistor. In such a case, the resistance of the second resistor become half of the resistance of first resistor. That is, as the area of cross section get doubled, the resistance become half. From this we can give the relation for resistance and area of cross section as R is inversely proportional to area of cross section of the resistor. That is, resistance is inversely proportional to the area of cross section of the resistor. If area of cross section of the resistor get increases, the resistance of that resistor get decreases. Let's say if the area of cross section of the resistor get decreases, then the resistance become large. That is, if you take these two wires, this is a thin wire, this is thin wire, right? And this is thick wire. Now, thin wire will have more resistance. Why? Because the area of cross section is less. The thick wire will have low resistance because its area of cross section is high. So that R is inversely proportional to A. Done? Yes. We see one more factor that affects the resistance, that is nature of the material. Here you can see that we have taken the two cases. Let's say in first case, the length of this wire is L. The second wire is also having the same length, let's say L. And area of cross section of these two wires are same. And the temperature is constant. That is, let's say both the wires are at same temperature. Okay. But only difference is nature. Let's say this is a copper wire. Let's say this is a copper wire. Let's say this is a steel wire. This is steel wire. Now we can see that the length, area of cross section, and temperature all remain same in both the cases. Only difference is you can see the difference in nature of the material. You all know that each type of material will have a different density, right? Different material will have a different density of particles, so that the resistance of one material is differed from the other material. So that if there is a change in the nature of the material of the resistor, the resistance of that resistor also will vary. So that finally we can say that nature of the material of the resistor will affects the resistance. Resistance depends upon the nature of the material of the resistor. Okay. Yes, this is the third factor. And next, we see the fourth factor that affects the resistance. What is the fourth factor? Temperature. Okay. Let's say if you have, let's say this is the first case, right? We have taken a length of wire or resistor L. Okay, here also the length of this resistor is same, whereas the area of cross section in both the cases is also same, but here the temperature is not constant. Let's say the nature of the material is also same. Let's say this is a manganese wire and this is also a manganese wire, whose length and area of cross section are same. But the resistance of the first wire, let's say 10 ohms. The resistance of second wire, assume that the resistance of the second wire is 20 ohms. Now you know that the resistance of this wire is greater, that is R1 is greater than R2. Now if you allow the electric current to pass through this resistor, okay, in both the cases, if you turn on the key and if the current passes for same interval of time through the different resistors, then at, let's say the current is paused at the same intervals of time, let's say for 10 minutes. Assume that we allowed the current to pass through this resistor for 10 minutes and this also for 10 minutes. After 10 minutes, if you observe, sorry, here R1 is greater than, less than R2, right? Yes, sorry. This is 10 ohms, this is 20 ohms. Now you can see that after 10 minutes, if you observe the temperature of the resistor 1 and the temperature of resistor 2, the temperature of second resistor will be greater than the temperature of first resistor. That is, temperature of first resistor is less than the temperature of second resistor. Reason is its resistance is large. If resistance is more, the upflow of, that is opposing the flow of electrons in the conductor is also more. So that most of the electrical energy will get converts into the heat energy. So that as the resistance is more, the temperature change is also more because of large emission of heat energy, because of large opposition of flow of electrons due to the high resistance, right? So that we can say that R is directly, finally we can say that the relation between the resistance and temperature is directly proportional. Resistance is directly proportional to the temperature, okay, temperature of the resistor. Done? Yes. And next, we see a law of resistance. Here, the law of resistance is nothing but, here we already know how this resistance depends upon the length, and how the resistance depends upon the area of cross section. Resistance is directly proportional to the length of the resistor. So let's say this is equation 1, and resistance is inversely proportional to the area of cross section of the resistor. Let's say this is equation 2. So from both equation and 2, that is 1 and 2, we can say R is proportional to L by A at constant temperature. At constant temperature, at constant T. Okay. So this we call as law of resistance. Now from this expression, we can say that R is the resistance, L is the length of the resistor, area A is the area of cross section of the resistor. Let's say resistance is directly proportional to the length of the resistor and is inversely proportional to the area of cross section of the resistor at constant temperature. We call this statement as law of resistance. Law of resistance. Okay. Now, so as we have a relation, what is the relation that we got here in the law of resistance? R is equals to, here I will write, R is proportional to L by A, right? So in the place of proportionality, here this equation or this expression is further written as R is equals to rho L by A. This is rho. This is the symbol rho. Okay. This is a proportionality constant we used here in this mathematical expression. And this is named as resistivity. What do you call this? Resistivity. Resistivity is also an electrical property of a conductor which opposes the flow of electrons through it. So it's just like a resistance, but there is a small difference between resistance and resistivity. We will see about the resistivity in the next class. Okay. So now you can see the relation R can be taken as R is equals to rho into L by A. Here R is resistance of the resistor, rho is the resistivity of the resistor, L is the length of the resistor, A is area of cross section of the resistor. Okay. Yes. This is the formula that we got. R is equals to rho into L by A. Done? Yes. Based on this, we will see a few numericals. Let's say question 1. A wire of resistance. Okay. Twelve ohms. Let's say a wire of resistance 12 ohms uniformly stretched until its new length is 3 times. Its new length is 3 times. Okay. So here initially, let's say initial resistance, first when you take the initial resistance, let's say R1, it is 12 ohms. And its length L1 is considered as L, and its area of cross section is considered as A. Now, when this wire is uniformly stretched until its new length, let's say L2, becomes 3 times its original length, that is 3L. Okay, the original length is L, so that the new length is 3 times the original length, that is 3L. Assuming the volume remains constant, here as the volume remains constant, the area of cross section decreases. That is, you can take the new area of cross section as A by 3. A by 3. What is the new resistance? What is the new resistance? We need to find new resistance. Let's say R2. Okay. Now, I will use the formula R1 is equals to rho L1 by A1. Okay, what is the risk here? Rho R1, first initial resistance 12, rho into L by A. Let's take this as an equation 1. Now, we need to find the new resistance, that is R2 is equals to rho L2 by A2. We need to find R2, right? Rho into, here resistivity will be same. Why? Because the same material, same wire is stretched. L2 can be taken as 3L. What is A2 here? A by 3, right? A by 3. Now, further you can take this likewise. Rho into 3 into 3L by A, right? Yes. Now, you can get R2 is equals to rho into 9L by A. Fine, I'm going to take this 9 out. 9 into rho L by A. Now, in the place of rho L by A, okay, I can take 12. That is from equation 1. You see that equation 1. Rho L by A is equals to 12. So that in the place of rho L by A, I'm using 12. So 9 into 12. What you will get? 12 9s are 108 ohms. This is the new resistance. R2 is equals to 108 ohms. Done. Now, we see the second numerical related to the same concept. Okay. A cylindrical carbon rod of resistivity 3.5 into 10 power minus 5 ohm meter. So its resistivity is 3.5 into 10 power minus 5 ohm meter. Okay, the rod is 5 centimeters long. What is the length of the rod? 5 centimeters. So I want to convert this into the meters. So we can say 5 by 100 meters. That is 0.05 meters, right? And has a diameter of 2 millimeter. Here they given diameter is equals to 2 millimeter. What is milli? 10 power minus 3 meters, right? Yes. But we need R here. R is equals to d by 2. Radius is equals to half the diameter, right? So 2 into 10 power minus 3 meter by 2. 2 ones are, right? So finally what you will get? Radius is 10 point minus 3 meters. Now, when it comes to the question, what you need to find? Calculate the resistance of the rod. Resistance we need to find. So we got a formula R is equals to rho L by A, right? Here we got rho. What is rho value? 3.5 into 10 power minus 5 ohm meter into, what is the length? 0.05 meter by area. If you take the area of cross section of the conductor, the area of cross section of the wire or resistor or conductor can be taken as pi r square, which is in the shape of circle. So that you can take 3.5 into 10 power minus 5 ohm meter into 0.05 meter by, what is pi value? 3.14 into r square. Here r is 10 power minus 3 meter whole square, right? So further you can write likewise 3.15 into 10 power minus 5 ohm meter into 0.05 meter by 3.14 into 10 power minus 6 meter square, right? Meter and square get cancelled. Here meter and meter will get cancelled. Let's say I'm just taking it as 3.14 into, that is 1's approximate value I'm taking. So that finally what you got here, 1 into, that is 10 power minus 5 into 0.05 into, if you take this 10 power minus 6 to the numerator, it comes 10 power 6. It becomes 10 power minus 6. Now, you know that if you calculate it, you will get 0.5 ohms. 0.5 ohms, right? This is the resistance. This is the resistance of the rod, that is, which is approximately equals to 0.5 ohms. 0.5 ohms. Done.